Okay, let's start. So we continue with Enrico Barausse, who will tell us more about EMRIs in non-Kerr spacetimes.
Thank you, dear. Hi, everyone. I will now present some work in progress I've been doing with my supervisor, Luciano Rezzolla, about EMRIs in non-Kerr spacetimes. First of all, I will briefly review what EMRIs in Kerr spacetimes, although you have probably heard a lot about this during this meeting. So life in Kerr is easy because Kerr is a vacuum spacetime. It's a Petrov type 5 spacetime, and for this reason, geodesics equations are separable. And there's an efficient way to compute metric perturbations, namely Tiokovsky formalism. On the other hand, the treatment of the inspiral phase is hard, as you have learned from Lior's talk. And you have basically two approaches. The self-force approach, in which you look at the deviation from geodesic motion as an interaction of the particle with its own gravitational field. And in this case, you have to solve a geodesic equation with, on the right-hand side, instead of 0, you have a term depending on the metric perturbation h. And this metric perturbation is produced by the particle itself. As it is produced by the particle itself, it is diverging at the position of the particle, so you need a regularization procedure. And this is known in theory, but hasn't been implemented completely in practice, and no inspirals have been computed so far. On the other hand, you have a more practical approach in which you compute, it is called the adiabatic approach or radiation reaction approach, in which you compute the time variations of the three constants of motion, energy, angular momentum, and Carter constants. And you can think of the particle following a geodesics with evolving parameters. This approach is less general than the self-force approach, and there were some problems in the past with the Q flux, which seems to have been overcome now thanks to a recent formula by Sago. And this has allowed to compute the first waveforms in 2005 by Hughes and Rasko. So why do we want to go beyond Kerr? First of all, there are exotic alternatives to Kerr supermassive black holes, namely gravastar boson stars and fermion balls and so on, although I think the only viable alternative is nowadays a boson star. Then, even if the supermassive black hole is actually a Kerr black hole, there's a lot of matter around it. An accretion disk in AGNs, stellar disks. The dark matter density profile is peaked in the center of the galaxy, although I learned yesterday that dark matter shouldn't play a major role in the galactic center. At least it shouldn't be influencing EMRIs in a strong way. Anyhow, little is known about the strong field region close to the horizon. And what we should wonder is if EMRIs can be a tool to detect deviations from Kerr in this strong field region, because we should be prepared for surprises, in my opinion. So, our approach. First of all, we have numerical solutions of black hole plus torus spacetimes. These solutions have been produced by Markus Ansorg and David Petrov. Unfortunately, their program cannot handle astrophysically realistic tori. In other words, our tori are heavy, are compact, and quite close to the horizon. So they are unrealistic, but we think they are useful as a strawman to maximize the impact of astrophysical bountiness on EMRIs. Our approach follows in spirit and in methodology Glampedakis and Babaks. As you have learned from Costa's talk, they compared Kluge waveforms produced in Kerr and quasi-Kerr, that is Kerr plus quadruple spacetimes. And they found that waveforms containing the same frequencies are virtually indistinguishable by Lisa, unless I learned today, unless if you include the radiation reaction. And they call this a confusion problem. So I will make a summary of what we do. First of all, we integrate numerically geodesics, general geodesics in black hole plus Torus spacetimes. And we can label these geodesics by 3 parameters: the latus rectum, the eccentricity, and the inclination of the orbit. These quantities are related. Our motion is bound, so we have a maximum and a minimum value for the radius, and the maximum value for the inclination. So we can compute these 3 parameters in black hole plus Torus spacetimes. Then we can compute the kludge waveforms using this geodesic motion. We transform to quasi-Bayer-Lindquist coordinates, because kludge waveforms have been computed in Bayer-Lindquist coordinates. And we put a cutoff at the dephasing time in order to handle radiation reaction effects. And then we address the confusion problem. That is, we compare waveforms in black hole plus Torus spacetimes to their closest equivalent in Kerr spacetimes. I will explain now what closest equivalent means. So I will now explain briefly first what are kludge waveforms. Then I will recall what is the dephasing time. So what is this cutoff in time? And then I will explain how we choose the waveforms to compare one to another. First of all, what are kludge waveforms? So kludge waveforms are a dirty approximation, as you know. And so first of all, you identify your Bayer-Lindquist or quasi-Bayer-Lindquist coordinates if you are in a quasi-Kerr spacetime with spherical coordinates in a Minkowski spacetime. And then you use the quadruple or octuple or higher order formulas. And this amounts to using 2 wrong assumptions. First of all, you probably know that the quadruple formula in Minkowski spacetime is derived using the conservation of the stress energy tensor of the particle with respect to in a flat spacetime, which is an incorrect assumption, of course, in a curved spacetime. And then you use the green function of the D'Alembertian in a Minkowski spacetime, which is a wrong assumption too in our spacetimes. But surprisingly enough, you get a good agreement with Tchaikovsky-produced waveforms in Kerr. And so I think this is the natural preliminary approach in non-Kerr spacetimes, where of course you don't have, as you have learned from Costa-Stokes, Tchaikovsky formalism. So how long can we trust our waveforms, as we don't want to include the radiation reaction for the moment? So we consider, let's take an orbit having parameters P, E, and inclination Z. So we can compute the waveforms having corresponding to the orbit having these initial parameters, both with and without an approximated radiation reaction. The radiation reaction becomes important when the overlap between these 2 waveforms drops below 0.95, and this is just a value, but this is usually the value which is employed in building template banks. And we call this time the dephasing time. In Kerr, it's easy to compute this because we have kludge fluxes for the energy, angular momentum, and Carter constant, and these fluxes can be based on post-Newtonian expansions and fits to Tchaikovsky data. Whereas in our spacetimes, we don't have these kludge fluxes, but we can just identify the dephasing times of orbits having the same orbital parameters. That is, if we have an orbit having parameters P, E, Z minus in quasi-Bayer-Lindquist coordinates in our black hole plus Torus spacetimes, we pick up the dephasing time of the orbits having the same P, E, and Z minus in a Kerr spacetime. So one expects, probably you cannot see the figure, but one expects that the dephasing time is proportional to 1 over the square root of the mass ratio, and this, in fact, we checked this. Okay, now I will explain the machinery we needed to compare waveforms in black hole plus Torus spacetimes and Kerr spacetimes. First of all, let's recall what the signal-to-noise ratio is. If you have a signal, which is the sum of a waveform plus some Gaussian noise, you can write the signal-to-noise ratio for a template, which I call h hat, in this way. In particular, you can express the whole thing using a kind of internal product. It's an internal product weighted with the detector sensitivity Sn. And so you have that the signal-to-noise ratio is the internal product of the template with the signal divided by the norm of the template itself. In particular, you can replace S using this formula, and in practice you can neglect the noise, because in practice when you take sufficiently long times, you can put H here instead of S. So now using this machinery, I will explain what the overlap function is. If you have a template matching perfectly the waveform, you can substitute in the previous formula, and you get that the signal-to-noise ratio is exactly the norm of the waveform. Instead, if you have a template which isn't matching perfectly the signal, you can write the signal-to-noise ratio as the norm of the waveform times an overlap function, which is in a sense a cosine, because it's defined, the overlap function of two waveforms is defined as the internal product of the two wave functions normalized, divided by their norms. So what does this overlap function mean? If we overlap black hole plus torus waveforms and Kerr waveforms, this overlap function expresses how much signal-to-noise ratio we lose if we match filter a black hole plus torus signal with Kerr templates. That is, the overlap function is 1 if two waveforms are identical, and it is 0 if the two waveforms are completely uncorrelated. So what we do to compare Kerr and Kerr plus torus spacetimes? First of all, we want to compare waveforms having the same frequency content, having the same spectrum, because this was found by Costas and Stas to be the most significant way to compare the two spacetimes. So what we do, we compute kludge waveforms for black hole plus torus orbits, and we extract from these waveforms the frequencies of the R motion, the frequencies of the phi motion, and the frequencies of the theta motion. And it's always possible to define these frequencies also if you're not on the equatorial plane, because you can define some kind of approximate frequencies. In that case, I don't want to enter into the details. But once you have the periods or the frequencies of the R motion, of the theta motion, and of the phi motion for black hole plus torus orbits, you can solve these sets of equations, because you do have analytic expressions for the R frequency, phi frequency, and theta frequencies in pure Kerr spacetimes. And these frequencies depend on 5 parameters: the latus rectum of the orbit, the eccentricity of the orbit, the inclination, the spin of the Kerr black hole, and its mass. So once you measure from your numerical integrated geodesics these 3 frequencies, and you can solve this system in 3 variables chosen among the orbital parameters and the Kerr parameters. And of course, if you can leave the variables you are not solving for to their black hole plus torus values. Let me make an example to make things clearer. If you consider equatorial orbits, you have 2 equations. That is, you have equality of omega r and omega phi, and 4 variables to solve: the eccentricity and latus rectum of the orbit, and the spin and mass of the Kerr black hole. So you can either solve for P and D and compute the overlaps between waveforms having the same spin, mass, and frequencies, but different latus rectum and eccentricity. Or you can solve for the spin and mass of the Kerr black hole and compute the overlap between waveforms having the same orbital parameters and frequencies, but different mass and spin. So if our overlap is more than 95%, the waveforms are virtually indistinguishable by LISA, and we say there is a confusion problem either in P and D, if we are solving for P and D, or in A and M, if we are solving for A and M. So I will now present our results. We take, we are not claiming that these are physical spacetimes. These are physical realistic accretion disks, because our program cannot produce this, cannot produce yet these spacetimes. But we chosen these values to try to maximize the effects of the astrophysical bumpiness on EMRIs. So here we have a black hole, central black hole with a mass of 10 to the 6 solar masses, and the torus of 7 times 10 to the 4 solar masses. So it's a mass ratio of more or less 1 over 14. The central black hole is almost Schwarzschild. It's slightly rotating in the negative sense, but this is virtually 0. Whereas if you take J total over M total squared, that is, what is the A parameter you see from far from the, so the central black hole is almost Schwarzschild, whereas if you look at the system from very far away, you see an A parameter of 0.224. This A black hole plus torus is J total divided by M total to the power of 2. The disk is located at has inner radius over divided by the mass of the black hole of 9.16, and outer radius divided by the mass of the black hole equal to 10. So it's a it's a ring. It's not really a disk. I don't know what this physically could be, but it's a solution of Einstein's equations, axisymmetric and stationary solution of Einstein's equations. This epsilon parameter is the deviation of the quadrupole moment, the relative deviation with respect to the quadrupole moment of a Kerr space-time. That is the deviation, it's the epsilon parameter Costas was speaking about. That is, this should be 0 for a perfectly Kerr space-time. The other example I've been considering is an even more extreme example in a sense. This is the central black hole has mass of 4 times 10 to the 6 solar masses, and the torus is just 1/3 of the mass of the central black hole. The black hole is spinning quite rapidly, and also the torus is spinning quite rapidly. A of the black hole is 0.5, and A total is 0.7. In this case, the torus is inside the innermost stable bound orbits, because its inner and outer radii divided by the mass of the black hole is 1.4 and 1.5 more or less. So it's a very massive torus spinning very rapidly, very close to the horizon, and quite restricted in radial extent. Quite surprising, at least to me. It turned out that the epsilon parameter for this spacetime was much lower than it was for the first one. So from outside, the system is very similar to Kerr if you look at it from far away. In the end, this is something the author of the course should be looking in a while, but well, we should. On one hand, there could be local perturbations which grow unstable, but the time scale for these perturbations should be larger than the time scale we are looking at. On the other hand, there could be these are equilibrium states in a sense, but they could be unstable equilibrium states. But this has still to be checked. But our viewpoint is that this is just a Stroman, an exact solution of non-vacuum solution of Einstein's equations, and we are playing with these solutions to see what happens to EMRIs. This is definitely something we should be looking at anyway. What about the small guy? We take a solar mass particle or black hole or whatever you want. So I will first present results for equatorial orbits. So in my language, internal orbits. First of all, we don't want to consider orbits crossing the torus because we should have non-gravitational interaction between matter and the small black hole. And I call it internal orbits, the equatorial orbits between the torus and the black hole, and external orbits, the orbits on the equatorial plane, but outside the black hole plus torus system. So what we find, and I will now show the results, is that in spacetime A, we have both internal and external orbits, and we always have a confusion in the parameter A and M, whereas we have a confusion in P and D, in a sense, the confusion which Stas and Costas found in their quasi-Kerr spacetimes, only far from the system. We don't have this kind of confusion because for internal orbits because of strong field effects. On the other hand, for spacetime B, as I told you, the ring is very close to the horizon, so we don't have internal orbits because the ring is internal to the innermost stable bound, is internal to the separatrix, internal to the innermost bound stable orbits. So we have just external orbits, and what we find is qualitatively the same as for spacetime A. That is, we always have a confusion in A and M, but we have a confusion in P and D only far from the system. I will enter the details now. So let me spend 2 minutes explaining this figure. Here on the x-axis, we have the latus rectum of the orbit, of the black hole plus torus orbit, multiplied by the sign of the orbit. That is, we have a positive latus rectum for prograde and a negative latus rectum for retrograde orbits. Here we have the eccentricity of the black hole plus torus orbit. In this plot, you can also see in red the separatrix for a black hole having a mass equal to the total mass of the system and a spin equal to the total spin of the system. The separatrix is the location of the innermost stable circular orbit. Whereas this blue dashed line is are the orbits which hit the outer edge of the torus from outside. What I plotted here is the overlap between waveforms having the same frequencies and having the same A and M, but having different latus rectum and eccentricity. That is, I solved the equations I showed you before in P and D. So these are waveforms having different latus rectum and eccentricity, but the same frequencies. And what you see is that the overlap is 0.99, far from the hole, then drops. And when you go close to the torus, you don't get any confusion. The overlap goes virtually to zero. And this is because of strong field effects. You can do the same for internal orbits, and as you see, the overlap is always very low. So in principle, if you could measure, it seems like you don't have any confusion. That is, it seems like even on the dephasing time scale, you could see the difference between these black hole plus torus spacetimes and normal pure Kerr spacetimes. On the other hand, if you compare waveforms having the same P and D, but having different A and M, in order to have if you solve the equations I showed you in A and M instead than on P and D, you get an overlap which is always more than 0.99, except for this small region here where the system of equations has no solutions. So waveforms having the same frequencies but and the same latus rectum and eccentricity are completely indistinguishable. And almost the same happens for internal orbits. I tried to do the same for non-equatorial orbits, and in this case I solved the system of equations for the equality of the frequencies in A, M, and P, and I got these results. That is, the overlap is very good far from the hole, far from the system, but when you go close to the torus, there is a region where you cannot solve the system of equations. So in this region, in principle, the two waveforms are different. So summing up, we have a confusion problem we found a confusion problem in the orbital parameters P and D, only far from the black hole plus torus system. Whereas we found a confusion problem in the black hole spin and mass in most of the space of parameters, in most of the space-time, if you want. How much is this relevant for LISA? Can this affect, because in principle one may say you have a confusion problem in the black hole parameters A and M, so you could have an impact on the measurement of A and M. Well, I don't think this is relevant for LISA because Arthur-I are still quite physically unrealistic. They are too massive and too close to the hole. But to confirm this and to really explore the effect of a disk on the waveforms, we need first a more realistic tori that is either larger, more extended in radius, or lighter. And I think this is quite a realistic goal. And the other thing is the inclusion of some radiation reaction, which I think is a much harder task. I mean, we could include quite easily post-Newtonian expressions and fluxes for the energy and the angular momentum, but we have no clear idea of how to proceed for non-equatorial orbits, because in that case you just have two constants of motion, E and L, and you don't have a Carter constant that we evolved. So we are thinking about this anyhow. That's all.
Okay, time for one question.
I'll start with a comment. When you use kludge, you should be very careful when you're approaching very close, okay? Because whole idea about kludgeness, it breaks down at Signaltonoise rectum 6 or so.
Sorry.
The kludge waveforms they're not applicable at anything around 6 m and or closer, okay? So, and my question is, how much do you need to deviate A and M in order to fit orbital frequencies? Let's say for equatorial orbits.
For equatorial orbits. So, of course, when you have, well, okay, let's start from this. Okay, this is for the epsilon equal to 0.11 case. In this case, as you see, you have to deviate M of a very small value, 0.01, 0.003, and so on. And yeah, it's a ratio, delta M over M total. Okay, and well, sorry. And this, how much I have to deviate A, delta A over A total to get the same periods. This is for the 0.11 epsilon equal to 0.11 case. You're right. On the other hand, where I have epsilon equal to 2.1, I have to vary delta M total. Delta M, I don't have to vary a lot, actually. Because as you can see, the figures are not very different. But I have to vary A lot. Because this is A total plus delta A, and A total is 0.22. So we have to vary A lot. But this is because we chose a very high epsilon. 2.1.
Okay,